It is going to be divided into two parts. The first part will be the execution in Mare Nostrum 4. I will guide you to, I will show you uh, how to uh, execute your application, your parallel application with PyComps into Mare Nostrum 4, as well as I will give you some hints on the tracing analysis overview with Paraver so that you are able to analyze the performance of your application uh, when after it finishes. Okay, so the first thing that you should have is close to you the user and password that have been provided to you to connect to Mare Nostrum. Okay, so for this tutorial, I will be in parallel doing showing the examples so that you can follow what I'm doing during the execution. And I will copy and paste the commands that I use into the chat so that you can also grab them from there and, and copy into your terminal, okay? So the first thing that we have to do is to do SSH. Don't forget -X, capital X, in order to get the graphical display that we will use at the end. Okay, so this is my account, and I will do SSH. Okay, now, so let's continue. If somebody else has issues, please write the issues in the chat or your question, and we will go dynamically answer them. Okay. Okay. Now that we are inside, the first thing that you should do is to edit bashrc. I don't know if you are familiar with BI or Nano. You can use the editor that you like. For instance, I am going to use bi.bashrc. You see my screen? Okay, so if you edit BI, you have to include module load comps 2.8 at the end of the bashrc. Okay. And once it is added, we should do source.bashrc. Okay. Now the next step is, as in the slide that you see in the background, you should go in, since you are in your home folder, do a copy of the sources that we are going to use in this tutorial. I'm going to paste it into the terminal, into the chat, and this will copy a folder called source. Okay. Any issue until now?
Yes, thanks, Aldo. Yeah.
Okay.
So you can copy paste this way.
Okay, so now that we are here, let's start with the examples, and then we will continue with one or two exercises depending on the timing. Okay, if we go inside examples, see the examples. Here you will see that we have 6 folders, 6 example application. Let's start with Cholesky. Okay. Julian is asking to do a PWD to check the location we should point to. It's this one, home NCT 000. Don't forget when cp-r, copying the dot which is at the end to copy the whole folder. Okay, so many of you are wondering how to execute the PyComps application, PyComps parallelized applications into a supercomputer. And we have been playing with Jupyter Notebook, which was running inside your local machine, inside your container. When we are in a supercomputer, there's a difference that there's usually a queuing system. Like, for example, in Mare Nostrum, we have Slurm that can be checked with the SQ, the status of the jobs that we have submitted. For instance, I haven't submitted any job yet, okay? And in order to ease the submission of PyComps jobs, we provide a command which is called enqueueComps, like this. If you run this command, then it will show you all the help and parameters supported by comps, enqueueComps, okay? One of the most important things is that it has the execution time to define for the job, the queue reservation, and it allows us to set the number of nodes that we want to use and many other configurations that can be used to tune your job. In this particular machine, we are using a Slurm, but in other machines that they have other queuing systems like PBS or Torque or whatever, there's a configuration into the comps installation that can be switched for another queuing system, so that the scripts that you have with enqueueComps work in any machine. Okay, so you don't have to deal with a Slurm or any other queuing system by default. Okay, so taking this into account, you will see that there's a ton of flags that can be used. And this command, enqueueComps, is common for Java, C, and Python applications. Okay. Within the Cholesky folder, there's a launch cholesky.sh script. Okay. If we see what's inside, here you will see that we have some variables for the execution file. We would get some parameters because this script accepts some input parameters for the number of nodes, the execution time, which is the wall time for the job, and if we want to get the parameter trace to analyze the performance. And then we have the enqueueComps that I told you a second ago. This enqueueComps is already prepared with some parameters that are very interesting for this execution. For example, we want to run in the back queue because these jobs are for testing purposes. We are going to run with a reservation that allows us to have a set of nodes specific for this tutorial, and we are going to use a number of nodes. For example, we can request 10, 11, or well, in this reservation, there's no more than 10, but we can request the number of nodes that we want for execution. The execution time, which is the wall time, and we have, for example, we can set the master working directory where the master files are going to be stored at the end of the execution, the worker working directory, which can be configured to use the local disk of the nodes or a shared disk. For instance, in Mare Nostrum we have GPFS, but in other supercomputers there's Lustre for shared disk. But we can use the local disk, which is an SSD within the nodes, for the temporary files that are created and then transferred. We can define that we want tracing if we want to generate the task dependency graph. And there are other which are very interesting, like for the class path or the Python path, in order to include libraries in the execution. Finally, there's one last flag, which is the language of the application that you are going to run. Okay. At the end of this script, we have the explanation of the parameters that this for this application and an example that can be copied and pasted to execute. But before executing it, let's see how an application in a Python script analyzed with PyComps looks like, because until now we have just seen Jupyter notebooks. Here we see that the Cholesky, which we had an example in a Jupyter notebook before, the Cholesky, we see that what has been added to the main script are the PyComps libraries, the task decorator, the parameter flags, or the constraint decorator, and at the end, we will see that there's the synchronization. Okay, so we have a plain Python script with functions decorated with task and constraint decorator. In this particular case, the computing units is being taken from the an environment variable, okay, which for the creating blocks. We have the common known pod, RF, solve, triangular, and gem functions decorated with the task decorators. They returns NP and ERI. And at the end, we have the main code on circ, I forget circ, the Cholesky block function, which is the main function to perform the matrix decomposition or the factorization of the given matrix. Okay, so here in the main code, you see that there's no synchronization at all, because it is at the end in the comps barrier. Okay, so what it is here, comps barrier. What I want you to notice is that we have a sequential Python code that we have included the task decorator, the constraint decorator in this particular case, because we want it. And at the end of the parts, for example, for the matrix generation, we have a barrier. And at the end of the Cholesky, we have another barrier to measure the times. Okay? I see that there's a question. How do you exit the file after opening it with VI? You should put a double, I think it's column, and Q, yes. And if you don't want to save, this is for reject the modifications. And if you want to save with WQ, it saves and quits. Okay. In this application, we see here that there are 3 parameters which correspond for the matrix size, for the block size, and the MKL threads that we want to use. You may see that the MKL threads is the same that we are going to use as for the constraint. Okay, so now that we have our application, which is a plain Python script, and we have the decorator and the synchronization, we go to the launching script, we copy the example, we are going to execute with 2 nodes, 1 master and 1 worker, during 10 minutes. If it takes longer than 10 minutes, the queuing system will kill it. We don't want to get the trace, and a matrix size of 4, block size of 512, computing units 8, and MKL 16, and if we want to verify the results. So if you copy and paste this command, it will say that the job has been submitted, a batch job. Okay, we have here a resume of the parameters that we can check, and the job has been submitted. Now that has been submitted, we can check its status with SQ. Okay, and we see that the job is running in nodes 41 and 42. Okay, while it is executing, it is producing a comps and job ID err and comps and job ID out files. Okay, this contain the standard output and the standard error of the execution, and you can check it dynamically with tail. Well, or with cat. Mine has already finished, and we can see the output here. Sorry, here is more clear. We see that it started launching the comps application, executing Cholesky, starts the runtime, and we have the prints inside of the application. Okay. And this is how we run applications in a supercomputer. Okay, for this very first example. Any question until now? Okay. A couple of things. While your job is executing, you may see, if you do SQ, that the job is pending, for example. You can cancel the job with scancel and the job ID, which appears in the job. If you, for example, you forgot to change something and you have your job in the queue, you can cancel its execution. Okay? Okay, now we have run the Cholesky. Once we have the Cholesky run, remember that we have the task dependency graph generated. So as Jorge explained this morning, there's by default a folder called .comps in your home folder, see .comps here, where a folder with the job ID has been created. Inside this folder, you will find all logs if the bug is enabled, but you will find also things like the task dependency graph generated in the monitor, or if trace is enabled, it will generate a folder called trace where the parameter trace will be. If you go into monitor, there you will see that there's a complete graph sorry, that can be plotted. If you do comps gen graph complete graph like this, it will generate a PDF. And if you have done the SSH with -x, you can do means complete graph.pdf to check it out. It takes a while to open because it is using the X window, and we see a real execution of a complete workflow with internal parallelism that being detected by the PyComps runtime and executed in a supercomputer. Okay, so in a nutshell, a PyComps application is a plain Python script with functions that have been decorated with the task decorator to define the tasks. There are synchronizations in order to retrieve data to the master mainly for some computations or any other things. And with those two things in mind, the extra things like constraints and any other decorators that you may find in PyComps, with the enqcomps command, you are able to run the scripts in any supercomputer. Okay. What One of the things that we want also to you to know is that the Python scripts parallelized with PyComps can be executed in any other environment by changing the infrastructure configuration that Jorge has shown before. So the code will not change even the infrastructure change, because the only differentiation is the configuration of the comps runtime. Okay. Okay, let's go again into the source folder examples to see another one which is a little, or probably which is a more known example. If you go into k-means and go into SRC, here you will see that we have an implementation of the k-means, okay, which initializes randomly the data. This k-means is the same that we have seen in the Jupyter notebook. So then you will quickly see that we have again our cluster points partial task, our partial sum task, and our reduce centers task. Again, we have our has converged function and our generate fragment task. And in this case, we have the generate fragment as a task because we don't need to plot, or we are not intended to plot. Now we are able to run extremely big k-means with extremely large matrices, or even hundreds of dimensions, because in these supercomputers we have a lot of resources to run. Okay. Again, the code you may see is the same. The main difference with the Jupyter notebook, if you haven't noticed, is that there's no PyComps start and no PyComps stop. I want to remark this if you haven't noticed. The PyComps start and the PyComps stop is just for Jupyter notebooks, whilst for Python scripts, there's no need to. Okay? One cool thing of this is that you can run your code and with just the enqcomps, which is the one who is going to do the start and the stop. Okay, so we have our code, we have added the task decorator to the functions that we believe that they are going to be the tasks, that we think they are going to be the tasks. I'm going to save. And if I go back to launch k-means, you will see that it is pretty similar, if not same, just changing the execution file. Okay. And the other thing that also changes are the parameters that are going to be passed to the application. Okay, let's execute a larger k-means with 72,000 points of 3 dimensions. You can copy this command paste it this way, and the job has been submitted. Okay, if you do sq, mine is already running, and I can monitor its behavior dynamically with tail -f. Now we see that it has generated the points in 0.07 seconds until it has reached the number of maximum iterations with this number of parameters, taking 10 seconds to do these k-means. If we go back into the log folder, we see that another job ID has appeared. If we go inside, we see again that we have the monitor, and we can comps gen graph, complete graph again. This graph it's pretty big, and this command may take a few seconds. Okay, it is there. Now you can check it out, what has comps done under the hood. Wow, you see it is a very wide graph. Well, one thing that can be seen in this task dependency graph very quickly is that there are 10 iterations, and since we have a synchronization on each iteration, we see that there are 10 small 10 reductions that end up in the next spawning of parallel tasks. So what we see clearly in this graph is that the wider the graph is, the wider the number of tasks we get, the more parallel it can be executed, the application. Let's go with a more complicated example. We have a folder called Gromax, and inside you will see that there's also a launch MD for molecular dynamics. In this case, we are going to use some specific modules for Gromax, and we are going to use we need a worker working view to be defined for yourself. Please, if you are going to execute this example, please update this worker working directory with your working directory in order to get, well, in order to use your folder. It is also useful to put here shared disk. Okay. If you go into cdsrc, we have 3 files. We are going to use lysozyme in water.py. Let's take a look. Okay. This example is it follows the tutorial originally by Justin A. and Len Kuhl from the Virginia Tech. And what we have done here is to take that example and to add the necessary task decorator and binary and MPA decorators in order to parallelize the molecular dynamics until reaching the stage number 4 for energy minimization. Before looking into the task, we go to the main code. Okay. This application takes a dataset path where there are a number of proteins and is provided with where the output path, where the output or the results for the energy minimization have to be stored at the end of the execution. Okay, so on a very first step, it looks for the proteins in the dataset folder. So it just goes into the dataset path looking for files with PDB extension, and then iterates over all those proteins and goes calling GROMACS with different parameters. Okay, for example, in the first step, generates the topology, then defines the box, then adds water, and then adds ions for the solvent, and so on until the sixth step where it does the energy analysis. Here you will see that it calls different functions like generate topology, define box, add solvate, assemble TPR, replace solvent with ions, ensemble TPR, and energy analysis. And most of them, the outputs from one of them is the input of the next one. Okay, so we are generating the topology, and the topology generated here is going to be the input of the third step here, and so on. So now that we have the structure in mind and what it applies over each protein, we can go and take a look into the functions for each step. Okay, which is in the top. Step number one is for generating the topology. The common command to generate the topology is this one, okay, which is GROMACS PDB to GMX to generate from the protein and get the topology. So what we do here is we have a function with the binary decorator that Rosa introduced you this morning, and we configure that the number of the binary to be used is GMX and the flags to be used. Okay, you may see that the protein here, structure, and topology are the parameters defining the task decorator. And in particular, protein is file input, structure is a result of this binary generator, and the topology is also another file produced by this binary. If we go into step number two, again, we see that the binary is again GROMACS, but it requires a different configuration. In this particular case, is edit conf to define the box. Okay, this binary has a file input and a file output. The next step, number three, is again another binary which adds solvate, and you will see that the mode and the parameters with the file in and file out required. Step 4 is another call to GROMACS with GROMPP. Number 5, and number 5, it's a slightly different. Number 5 is an execution of GROMACS with MPI, so internally it's being parallelized with MPI, so that the task is going to be using a set of computing units. In particular, this execution of MPI run for GROMACS MPI, it's going to be using 24 cores. Okay? What does this mean? This means that we want GROMACS with MPI to be executed, and since we have 48 cores per node, our scheduler will be able to run two of this energy minimization in the same node at the same time, but no more tasks. And although there's the resources. Finally, this example finishes with a binary for the energy analysis, again calling GROMACS. So here we have a workflow, or more known as a pipeline, to do the molecular dynamics of a protein. Okay. At the end of the execution, we see that we could add a COMPS barrier, but since it is added automatically at the end of the execution, we don't need to add anything else. If for any reason we need something from one of the tasks, we should add here a COMPS wait on, get the value, compute and do something else, and print or do whatever. This application receives three parameters: the configuration path, the dataset path, and the output path. And these parameters are already prepared in the Python script. You will see that there are other full and only GMX, which are with MPI or complete, which generates pictures, but they are more oriented to be used with Matplotlib. Okay, so if we do cat launch md and we execute following the number or the reason of each parameter, you will see that now I'm going to run with two nodes, one master and one worker, maximum time allowed 10 minutes, and I want to generate the trace where the configuration file is, the dataset, and the output. Okay. Now it says that the job has been submitted. The job ID is here, and we can check with the queuing system that our job has been submitted and it is running. I forgot to put this command. We can see the execution, and the first thing that we see is that it has started extrae. Extrae is the application that grabs the events that are going to be stored in the parameter trace. The execution of this example is very fast, and it says that it has terminated and it has generated a trace file in the log folder. If we go into the output folder, we will see that it has generated a set of files that all of you who is familiar with GROMACS probably will know its meaning. But just for the sake of the tutorial, if we do module load grace and we do xm grace and we take one of the xpg, we will see graphically the energy analysis of the 1xyw protein, which is this one. So since this application, it is taking the proteins from a given folder, which is here in dataset, the more files that we put in this folder, the more proteins it will be able to analyze. And if we go back into .comps folder, if we go into the job ID, my 764, we can go again into monitor and do to check the graph. Here we see very clearly that, that COMPS has been able to extract the parallelism and do the analysis of the three proteins completely in parallel. However, each step requires from the previous, but PyComps has detected that it can execute the three proteins at the same time. Any question until now? I'm going to give a small spoiler for those of you who are um, thinking into the performance and how to demonstrate that this is going running in parallel. And within trace, we have the paraver trace that we enabled. Okay, if we open module load paraver, we load paraver with this, we will be able to analyze the performance. Okay, so now we can do wx paraver and the PRV file. If we go to configuration and we take comps tasks, for those of you may appear empty, go to load configuration. Well, probably it will be better to follow me just taking a look into the screen, and I will show you later on how to deal with this. Oh, sorry. We see the comps tasks. Now we see there are only a few tasks, but we clearly see that there are two nodes, and it has placed one of the MPI, which is for the energy minimization, and the other two in the same node, and one in another node. Because we are running with one master, taking half of the node as worker, and another one which is for the full worker. But this application has only a very few number of tasks. If we go again into source, we have a last example before going into an exercise. But yes, which is the clustering comparison. Probably you are interested on using the dislib. And the dislib can also be used within supercomputers. The dislib is, in this case, also installed and available into Mare Nostrum. And if you take a look into the launch cc.sh, you will see that the first line is module load dislib. This will make dislib available for comps for this execution. Okay. And if we go into SRC, we will see that we can use dislib as a library to perform any analysis that we want. For example, to do a k-means, to do a DB scan, Gaussian mixture, and other ones. What this application does is, from this lib cluster, it does these three algorithms over a set of different inputs in order to analyze its behavior under different circumstances. Again, it is very easy to launch. If you take the script and you get the example execution, we are going to use with two nodes, 10 minutes, and we want to get to get the trace. This execution will take, I think it's 1 or 2 minutes. Mine is running now. And the output will be a plot where we will be able to see the behavior of those algorithms over different distributions of points. Okay, so while it is running, cool things about the execution of PyComps with tracing, it also gets hardware counters. So in the trace, there's also information about the internal behavior of the resources. And my application, my execution has finished and generated the trace file. Here we have result.png, and we can display result.png, and we will see the result of the application. Okay, on the left, you will see a column with the k-means, in the middle with db scan, and on the right with Gaussian mixture. You will see, for example, that I think there's an issue here. Oh, it's something wrong here. The db scan has done something wrong. I'm sorry. Let me see for the previous executed source. Display result. Something wrong with my machine. Well, you see that the result provided by the application, and it can be tuned on your in the way that you want. If you go again into the source, we have already seen all but these two: Cholesky, clustering comparison, Gromax, and k-means. There's still word count and Mandelbrot left. Okay, so now I will give you a couple of minutes, well, a couple of minutes, 15 minutes, let's say 10 or 15 minutes, so that you can go into source and parallelize the same the word count into Mare Nostrum. Okay. To this end, you will find that there's an src folder here, and within there's a wordcount.py file. For this exercise, you will have to include the appropriate decorators, the appropriate parameters, and the necessary synchronization call for COMPSs. And once you have the file modified, you can go into the main folder and you will see that there's a launch.sh that will run the application sequentially, and there's another script with launch with pycoms.sh, which will run the same script but with pycoms. Okay? Okay, let's continue. Have you been able to do it? I guess so. It was very easy, no? If you go into SRC and you edit word count, what you need to do is to do on pycoms.api.task import task. From pycoms.api.parameter import file in, and from pycoms.api.api import comps wait on. These are the three imports that we will need to parallelize this application, if you remember. The first one is to add the task decorator to the read file, and file path is file in, right? The next task is the word count function. In this case, we need to add the task decorator and returns. What does this return? We are executing using Python 2, so by default. So in this case, we are going to add that this returns a dictionary, which is partial result. It contains the words and its number of appearances. Sorry, I'm going to... Okay, and finally, we have the merge two dictionaries function, which is also another task, and returns a dictionary. With these changes, we have already defined the three tasks for the word count. And now we need to synchronize the results. One usual way easy way to detect when to do the synchronization is to take a look when you need an elapsed time, which is the final of the algorithm. If you do result equals comps wait on result, it will wait in this line until the result has been computed, and then the next line will compute the elapsed time. Okay, now let's try to execute it. If we go into the source and we check launch with PyComps, now we are going to run a larger data set. For example, we can take, oh, this path is wrong. This path is 0, 0, 12, and there's a set of data sets. Let's take the largest, 256 files of 16 megabytes, which is more or less 8 gigabytes. And we want to get the trace file to see how long it takes. And we are going to execute using one master and two workers. This is the command that I have submitted. I'm going to paste it here in the chat. Now it seems it is starting. As you see, it complains very quickly when something wrong happens. And when something wrong happens, it is a good thing to do to enable debug mode and to go to the log files and check what has just happened. It has taken 21 seconds in executing a word counting with more or less, I think it is 8 gigabytes. Let me check. Eight gigabytes, which is pretty fast. Of 8 gigabytes of plain Python, plain text, sorry. Now you can go into the comps.comps folder in your home, and you can go to the job ID you will see that there's no issue here, and you can go inside trace, and we can get and show here a more a larger trace than previously with more tasks. If we open the trace, and we see the comps tasks, in the y-axis we see the number of cores and nodes. So number 1 is the master, 1 is the worker in the master, which is 24 cores, and we have another node with 48 cores and another node with 48 cores. We see here the tasks that have been executed and their timing. We will see more information about this tracing analysis later on. We see that the blue corresponds to read file tasks, and the white to the word counts, and the red ones for the merges. Okay? So you see clearly how it has been parallelized over the available resources. Okay. Let's continue with a more difficult exercise. In the same folder as the word count, you will find a malneighborhood.py file. If you take a look inside, you will see that this is a plain Python implementation of the Fractal Generation, okay, with a set of predefined parameters. If we go to the main, it executes the main to generate a fractal, and the two exercises that are proposed for the next minute are exercise 1, which is to parallelize the fractal generation, which I'm going to give some tips right now, and the next exercise is that I will guide you with this exercise step by step, which is to add number, to add a slightly more performance boost. You will see here that there are two functions. You must choose which of these two has to be selected as task. Okay? I'm going to give you another 10 minutes to take a look at this code, and after that time, I will give the solution to this application. Of course, if there's any question or anybody wants to start a discussion, it will be good for everybody to talk about this. And also, I forgot to say, if you want to launch it, there's a launch with PyCon's mandel, which is already prepared for you to run with the necessary modules to generate the fractal. You just need to run with the number of nodes you want to use, the number of minutes, and if you want to get the trace file. Okay, let's solve this. Okay, let's answer Minho. If it shows that you cannot, that the connection has been reset, is that you have probably that you have put wrong the password too many times, and probably you need another account. Okay, so let's focus in the exercise. Okay. The first thing that we have to do is to import PyComs. To this end, we will need from pycoms.api task import task, which is the main decorator that we use for parallelizing with PyComs. And as well as you can imagine, we will need to synchronize. So we can now import from pycoms.api import const wait on. In this application, we are not dealing with files, so I'm not going to import any other parameters. Many of you may ask why there's a matplotlib use AGG. This is because for saving files, plot files, it is necessary in Marinostrum. And now let's go for the main question. Which of these two functions has to be a task? For those of you who have thought that this is a task or can be a task, you may be right. But the content of this task is really small. The best solution to this exercise is to define as a task the Mandelbrot set, which computes a fragment of the image of the fractal and has enough duration to make it worth the offload of the task to the nodes. What it returns is a list. Okay, is it right? And what it does is it calls to all elements in a range to the Mandelbrot function. Okay, but we are still missing something, which is the synchronization. The synchronization has to be in the main code after the for loop, which loops over the fragments of the fractal. And in this case will be z equals comps wait on z. Okay, let's try to run this code. We are going to uncomment this line, and what is this doing? It is adding the time required to generate the fractal in sequential mode, and then it will add the time to generate the fractal with PyComs. At the end, it will create a plot with a time comparison. Okay, so let's run it. Launch with PyComs Mandel. We are going to use one master with one worker. So one master with half worker and one full node, so 2 nodes without tracing. My job is running. And let's see if we can get benefit from using PyComs. As you have guessed, this application will run first the fractal generation without PyComs, and afterwards it will run it again with PyComs. Oh, something has failed. An exception occurred. Mandelbrot set PyComs. My fault, because there's something which hasn't been defined. BIC Mandelbrot. It is saying that there's an issue in the main code, and this function, Mandelbrot set PyComps, doesn't exist. In order to avoid this, I'm going to copy this function completely, and I will be able to have the sequential and the Python version. The sequential and the Python version. This is completely the same as doing this. Return Mandelbrot set ex max p. For those of you who are wondering why I'm keeping both. But for this exercise, I'm going to keep the code duplicated. And if I run it again, it is running now. A new file out has been created. I can advance that the execution is sequential. The sequential execution of the Mandelbrot fractal generation takes more or less 100 seconds. And while it is running, what is happening under the hood? During this in this moment, it is running it in sequential. And once it finishes, it will do the same work, but running in parallel with you can check with BSC load and the job ID. You can check how the resources are being used. And the application has finished. And this is very interesting. If we show the output, we see that the sequential fractal generation has taken 107 seconds, while using PyComps, it has taken only 5 seconds. So this is the benefit that you can gain with a good parallelization with using PyComps, and this is the benefit that you get. So for everybody who is aiming to use PyComps and parallelize their applications, we are also interested in seeing your code and trying to get the best performance in distributed environments. So this is a very graphical example showing the benefit that you can get. And if you want a graphical image, you can display time comparison PNG, and you will see the time required. Takes a little bit. Sequential more than 100 seconds, and with PyComps just a few. And the second exercise, which I'm going to guide you, is to try to do it slightly faster. Can we do it in less time? Yes, we can. If we use also Numba, because Numba is very good doing this kind of functions, like the Mandelbrot function. So if we take the Mandelbrot function, we copy it, we git compiled from Numba import git, and we take the task. I'm going to copy again to have a third task, and we call set PyComps with Numba and add the flag number equals true, with number, let's see what happens. We launch it again. While it is running, we can check the previous execution. Fractal, for example, we can compare the sequential with the PyComs1. As you may see here, the fractal generated is this way. And if we compare with the sequential, well, in fact, they have exactly the same size. So they are exactly the same as we expected. And in a couple of minutes, oh, something wrong happened. Oh, yeah, I see. I see what has just happened. I haven't changed the name of the function, Mandelbrot. It is in the same way. So this is Mandelbrot number, and this is Mandelbrot number. One interesting thing that number isn't able to, the reason why I did compile this function is that number with PyComs, it's only, well, number is not able to compile inner functions. So this will make this task to be compiled with number, and since we are calling another function, we are going to git compile this function again so that it can get more performance. This is the reason that I forgot to mention before. So now let's wait a couple of seconds and the results will appear. The sequential part is taking longer than expected. 107. Let's see with PyComs how much it takes. Should be around 10 seconds, 9 seconds. And with number 1.9. So now you see, and this is like the cherry of the pie. Sequential is slow. Using PyComs, you can get, with a proper parallelization, you can get a good performance. And even if you use any other, or if you use one of the extensions of PyComs, you can even get more performance. The clearest image display time comparison. Yes, I will show you in a second. Display time comparison, you will see graphically the same results that we have. If you want to copy this source code to your local machine, you should do from your machine, you should do scp the user, which is your user, which is nct 01xxx at mm1.bsc.es, 2 points. whatever, for example, and where do you want to copy? Sorry, this like this. Don't forget to change the X with your user, okay? So to end up with this session, I want just to give you a very brief overview of performance analysis of the traces. I have given a few spoilers previously, but this is more detailed information. As you may have seen, COMPS is able to produce performance traces for paraver, like this one in the picture, where the y-axis represents the number of cores where it is being executed, the x-axis represents the time, and the colors identify the tasks that are being executed. For example, in this example, we have the word count in orange, the first green is read data, and the light green is the mergers. We can see here that the priority flag that we were talking yesterday, it's being made use of by the scheduler, which is able to make some of the reductions before doing other reads and other word countings. This tool, Parameter tool, is also belongs to it's also provided by BSC, and there's also it is very powerful tool which has a lot of features for tracing for performance analysis. How it works? The way it works is that each task emits the events, and the file transfers are also events that are recorded during the execution. During the execution, an XML file is created by the workers to keep track of these events, and at the end of the execution, all these files are merged to get the final trace. To this end, to get or to harvest all these events, we use the extract tool, which is also part of BSC, provided by BSC, and dynamically instruments the application. For example, in a worker, extract keeps track of the events in an intermediate file, and in the master merges the intermediate files with the master file at the end of the trace file. And during the execution, it is able to get even performance counters, which are sometimes very interesting to analyze the performance more in depth. As you may have seen, there's a header and a footer during the execution, showing us that we are in starting extract and doing the merging at the end of the execution. And in the middle, you will see the prints that the application may be spawning in the output. As you may have seen, the trace file is generated within the .comps folder of your home directory. How can we do that? We can do installing Paraver, and we can go and execute wx Paraver over the PRV file, and we provide a set of configuration files which are within the installation of COMPS, or in the case of Mare Nostrum, are in this path, that can be used to automatically generate this graph for each task. We provide a lot of configurations that are specified and are explained in the documentation of COMPS, and they are growing every day. Paraver allows to fit window by time, view the event flags, so that with these green flags you know that there's something when it starts and when it ends. And it is able to show an info panel to identify the task with colors and even another labels for timings. In addition, it allows you to zoom in or zoom out to try to identify any kind of thing or issue that may have happened. And you may see that it is useful to detect when the processor is idle, which is the black parts that appear between tasks. So the shorter they are, the better. Summarizing the lines in the thread correspond to the cores that are being used. The colors mean black idle, the resource is idle, and other colors a task is running, and the flags correspond to the events that may be emitting. So with this, I finalize this session.